Alright, now we're on to chapter 21. And to start with chapter 21, we're going to talk about phenols. So first of all, what is a phenol? Well, the phen part refers to a benzene, because we sometimes call benzenes phenyl rings. And the ol part simply refers to an alcohol on that benzene. So a phenol is just a benzene with an alcohol on it. Now, usually the first set of questions you're going to see regarding phenols are about acidity. And let's start by asking, well, how acidic are phenols to begin with? Well, think about what happens. We know in acid-base reactions, some base comes in. Let's say we have an OH minus here. That OH minus will grab a proton, and the best proton to grab is that OH. And so the electrons go to the oxygen, and you're left with O minus. And of course, that O minus can then resonate throughout the benzene ring. One step around, this can swing down, and the electrons end up in the ortho position over there. And so you have a resonance structure that looks like O double bond and a negative charge over here. And of course, that negative charge can resonate down. The electrons swing over here, and now we get a negative charge in the para position. And finally, this negative charge can do another one of these arrows, swing to the side, and the electron can move up here. And we have one last resonance structure, where you have the negative charge on the other ortho position over here. And this resonance and the negative charge being in the ortho para positions will be important when we talk about some acidity trends. So the next thing I'm going to talk about is very similar in what we were talking about with the amines chapter on benzene, with nitrogens on benzene, when we were talking about basicity. Namely, what happens if I have electron donating or withdrawing groups on the benzene, along with that OH. So let's say I draw out a couple phenols. This one, another one, a third one, let's do a fourth one for good measure. And I'm going to add some electron donating groups and withdrawing groups, and we're going to talk about who's most acidic, who's most basic. So I'm going to draw an NO2 over here, and remember NO2 looks like this. So you'll either see it with it drawn out, or sometimes they'll just be lazy and write NO2, but this is the same thing. Let's put an OCH3 group here. Let's put an NO2 group here, and we'll just leave this regular old phenol. So in the amines chapter, when we were talking about basicity, we said that electron withdrawing groups make something more acidic, because an acid accepts electrons from a base. It becomes negative when that proton is removed, and therefore an electron withdrawing group can better pull those electrons and help stabilize them. Electron donating groups, on the other hand, make things more basic. Bases want to give up protons. They don't want to give up protons. They want to take protons, and they need electrons to go out and grab those protons. Another way of thinking of it is, well, I just said it actually, they need to use their electrons to go out and grab a proton. So if you have an extra set of electrons being forced into your system, that makes it more basic because there are more electrons to do that grabbing. So now let's apply that to this. Let's start with this phenol. In every situation, we know that the OH is where the hydrogen is going to get pulled off. And I'm going to actually start from this side. So this doesn't have any withdrawing groups or donating groups other than the OH, but every structure has the OH, so we can't really compare it just on that. We'll come back to this and see how it compares to the other three in a second. NO2. We said NO2 is a good, strong electron withdrawing group. So this would make the phenol more acidic, because we said electron withdrawing groups make things more acidic. They're pulling electrons towards the nitrogen, so when this becomes O-, that those electrons have somewhere they want to go, towards the nitrogen. OCH3 is a decent electron donating group. So this will have the opposite effect. If this oxygen becomes negative, those electrons are going to want to resonate into the benzene, but the lone pair of this oxygen is also trying to resonate around in the benzene. So those two negatives aren't going to want to converge. That hydrogen is not as acidic for that reason because we don't want to make that oxygen negative. It will have to share the benzene ring with the resonance between the two oxygens. So we can probably say that this is the least acidic. But now, comparing the first structure to the third structure, both of them have NO2, and we said that makes it an acid. Because we have, or it makes it more acidic because we have a good withdrawing group. But how does this compare to this? Well, let's draw out the NO2 here as well. And let's look at how things resonate between the two structures. Let's say that hydrogen gets pulled off and we're left with the O- like we were talking about before. We saw that the electrons of the oxygen can swing down, form a double bond, and these electrons can move around like this. Now, we saw that eventually these electrons can end up on that carbon there, and we'd be left with a negative charge there. So let's draw that out actually. We would have double bond O, this double bond is the same, this carbon is now negative, and we have a double bond there. Right? That was the resonance structure we were looking at before, but now there's an NO2 over here. Now, can that NO2 stabilize that negative charge? Yes, it can, because this negative charge can resonate down, and the electrons of the oxygen can swing up. This looks kind of like the enolates we were discussing with chapter 19 and 20, meaning we have an O-, or in this case a carbon minus, on a double bond like that. Sure, it's N double bond O, but the idea is still the same. Electrons can swing down and this can go over there. So that's what we're doing here. Same exact thing. And so having an NO2 in either the ortho or the para position will help stabilize your conjugate base. So we know that at the very least, this is probably a very stable conjugate base, and stable conjugate bases have strong acids. So this might be the most acidic, but let's see what number 3 has to do before we say that for sure. With number 3, we said the negative charge will either end up here or here. Those negative charges are too far away from the nitrogen to resonate with that double bond O. As a result, the only resonance you can have with the negative charge that ends up on this oxygen would be within the ring itself, resonating around the ring. But it can never resonate into that nitrogen because the negative charges will end up too far away. So even though this makes it a little more acidic being an electron withdrawing group, it doesn't make it as acidic as structure 1 where you had the full ability to resonate into that nitrogen. So if I number this, structure 1, 2, 3, and 4, we can definitely agree that 2 is the least acidic because it has a donating group. And between 3 and 1, 1 is definitely more acidic than 3. But now, where does 4 go? Does it go before? Is it more acidic than 1 or is it more acidic than 2? Well, since this has neither withdrawing groups nor donating groups, it kind of falls in the middle of the two. So 4 should fall between 2 and 3. Because most basic, nothing to make it basic or acidic, so it's kind of in the middle. And then acidic, much more acidic. And so here's the general trend for this question. And that's really all the acidity questions boil down to when you're dealing with phenols. Is my electron withdrawing group in the ortho or para position? If it is, that'll probably be the most acidic structure. If it's in the meta position, it'll still be a little acidic, but not as acidic as if it were ortho or para. And then the electron donating groups will make it more basic because, again, we don't want to share 2 separate attempts at resonating with the ring, one from the oxygen that's already there and the one from the O- we're going to make. Okay, and that's about it for the phenol acidities.